Hello, welcome to my video series of data structures. This is part 2 of Module 8, the graph data structure. In this video, we will present the implementation of graphs. In the previous video, we introduced the fundamental concept of graph data structure. A graph consists of a set of nodes, denoted as V, and a set of edges, denoted as E. Each node can have an assigned weight and degree, while each edge can have an assigned weight and direction. In this video, we will explore the implementation of the graph data structure. The implementation should support the following fundamental graph operations. The add-node operation adds a node to the graph, and the add-edge operation adds an edge to the graph. The delete node operation removes a node from the graph, and the delete edge operation removes an edge from the graph. The update weight operation updates the weight of a node or an edge. The isAdjacent operation checks whether two nodes are directly connected by an edge. The listNeighbors operation lists all neighboring nodes of a given node. Finally, the getDegree operation returns the degree of a given node. We will illustrate the implementation using a directed weighted graph, as it is more complex than an undirected unweighted graph. Consider the graph shown here. To represent the nodes, we use a node array V, where each entry corresponds to a node in the graph. Since our graph contains 5 nodes, the array V will have a size of 5. Each entry stores information associated with its respective node, such as weight, in-degree, and out-degree. For example, V0 represents node A, which has a weight of 4, an in-degree of 1, and an out-degree of 1. Additional properties can also be included as needed. Next, we can represent the edges in the graph using two common approaches: the adjacency matrix and the adjacency list. We will examine each approach in detail. The adjacency matrix approach represents edges using a V by V two-dimensional matrix, where V is the number of nodes in the graph. Let M denote the adjacency matrix. Each entry, Mij, stores information about the edge from node I to node j. In a directed graph, Mij represents the edge from I to j. In an undirected graph, Mij simply represents the edge between I and j, making the matrix symmetric. In other words, we have Mij equals Mji. For example, M21 represents the edge from node C to node B, which has a weight of 19. Additionally, the entries in the adjacency matrix can be extended to store other edge properties as needed. The space complexity of an adjacency matrix is OV squared. As a result, this approach can be memory intensive when dealing with large graphs with many nodes. Next, we will discuss how to implement fundamental graph operations when using an adjacency matrix to represent edges. To improve efficiency, we introduce lazy deletion, a variant of the standard array deletion operation. In a typical deletion operation, removing an element from an array requires O(n) time, where n is the total number of elements. This is because all subsequent elements must be shifted to maintain contiguous memory storage. With lazy deletion, instead of shifting elements, we simply mark the corresponding array entry as null, avoiding unnecessary data movement. This reduces the deletion operation to O(1) time. However, scanning the array may become slower due to the presence of multiple null values. To mitigate this, we shrink and reallocate the array when null entries outnumber valid data entries. As the example shown here, when the array contains 3 null values, we can resize it by copying only the valid elements into a new array, effectively removing the null entries. As proven in array resizing operations, the amortized time complexity of lazy deletion remains O(1). Now, let's explore how to implement fundamental graph operations using an adjacency matrix. To add a node, we need to update both the node array V and the adjacency matrix M. Each node is typically assigned an internal ID, which corresponds to the order in which it was inserted into the graph. For example, node I represents the ith node added to the graph. When adding a new node, its internal ID should be set to the current number of nodes already in the graph. This means we must allocate a new entry in the node array V at the last position. We also need to allocate a new row and column in the adjacency matrix M to store edges related to the new node. The newly allocated space is highlighted in red in the node array and adjacency matrix, indicating that these operations take immediate effect. Here is the pseudocode for the add node operation. In line 2, we allocate the last position in the node array V. In line 3, we allocate a new row for adjacency matrix M. Finally, in the for loop between line 4 and 7, we extend every row in the adjacency matrix M by 1 position. Since each row in matrix M needs to be resized, the amortized time complexity of add node is OV. In the worst-case scenario, where resizing operations involve doubling the matrix size, the time complexity increases to OV squared. To implement the add edge operation and add an edge to the graph, we simply update the corresponding entry in the adjacency matrix M. In some cases, it is necessary to keep track of the degrees for each node. If degree tracking is required, we must update the out degree of the source node and in degree of the target node accordingly. This is the pseudocode for the add edge operation. This function accepts 3 parameters: the source node index I, the target node index j, and the edge object E, which may contain edge-associated information such as weight. In line 2, we store the edge object E in the adjacency matrix entry Mij. Then, if degree tracking is required, we update the out degree of node I and the in degree of node j accordingly. The next operation is delete node, which removes a node from the graph along with all its associated edges. In this case, to remove node I, we need to delete the ith entry in the node array V and the ith row and column of the adjacency matrix M. Instead of performing immediate deletions that require excessive data movement, we use lazy deletion. Specifically, we mark VI null, indicating that node I is deleted. The corresponding entry is marked red in the figure, meaning that the update takes immediate effect. Conceptually, we should also remove the ith row and column from M. But to avoid frequent data shifts, we leave these entries unmodified. The affected entries are marked yellow, indicating that the update will take delayed effect. When checking whether an edge between node I and j exists, we verify if Vi or Vj is null. If either entry is null, the edge is considered non-existent. Note that if the null entries in V outnumber valid entries, we need to shrink both V and M to optimize memory usage. Shrinking M requires OV² time, and it occurs after OV lazy deletions. As a result, the amortized time complexity for deleting a node is OV. Note that when deleting edges associated with node I, the degrees of all neighboring nodes of I should be updated. The affected neighbors of I can be identified by traversing the ith row and column of M, which requires OV time. Overall, the amortized time complexity of the delete node operation is OV time, while the worst case time complexity is OV² due to matrix resizing. Here is the pseudocode for the delete node operation. This function takes one parameter, the index of the node that needs to be deleted. In line 2, we perform lazy deletion by marking Vi as null. Then, in lines 4 to 7, we update the degrees of all nodes previously connected to node I. Then, we have the delete edge operation. To remove an edge between node I and node j, we simply modify the corresponding entry Mij. If degree tracking is required, we also update the relevant entries Vi and Vj to reflect the change. The accesses and updates of all entries can be done in constant time O1. Here is the pseudocode for the delete edge operation. This function takes the source node index I and the target node index j as input. In line 2, we modify the adjacency matrix entry Mij to remove the edge. In lines 3 and 4, we update the degrees of nodes I and j. Then we have the update node weight and update edge weight operations. To update the weight of node I, we modify the corresponding entry vi in the node array. To update the weight of the edge between nodes I and j, we modify the entry mij in the adjacency matrix. Both operations can run in constant time, O1. Here are the pseudocode for the update node weight and update edge weight operations. The update node weight function takes the index of the node that needs to be modified and the new weight as input. It directly assigns the new weight to the corresponding entry vi. The update edge weight function takes the source node index I, the target node index j, and the new weight w as input. It directly updates the weight of the edge stored in mij. The next operation, isAdjacent, determines whether an edge exists between node I and node j. With the adjacency matrix, this can be verified by directly checking the entry mij. This operation thus runs in constant time, O1. In the figure, the accessed entry is highlighted in blue, signifying that the data is being read but not modified. The following is the pseudocode for the isAdjacent operation. In line 2, it verifies whether the entry mij is null. If null, the edge does not exist. Otherwise, the edge is present. Additionally, the code can be modified to return mij directly, enabling the retrieval of edge-associated information, such as its weight. Then, we have the listNeighbors operation, which enumerates all direct neighbors of node I. This can be achieved by scanning the ith row of the adjacency matrix M and identifying all non-null entries. Scanning the ith row of the matrix M requires OV time. The following is the pseudocode for the listNeighbors operation, which takes the index of a node as input and enumerates its neighbors. In lines 2 to 4, it traverses the ith row of the adjacency matrix M, outputting all connected nodes. Finally, we have the getDegree operation, which retrieves the degree of node I. Since the degree of nodes are tracked, the operation simply returns the value stored in entry vi. Here is the pseudocode for the getDegree operation, which takes the index of a node as input and retrieves its degree. Since the degree is precomputed and stored, the operation simply returns the value directly, running in constant time, O1. Below is a brief summary of the time complexities for fundamental graph operations using an adjacency matrix implementation. Most operations run in constant time, O1, except for add node, delete node, and list neighbors, which require OV time. The second graph implementation is the adjacency list, which represents the graph as an array of linked lists. We denote this adjacency list as L, where L is an array of size V. Each entry, Li, corresponds to a linked list that stores all edges originating from node I. For example, the graph on the left is represented using the adjacency list L shown on the right. Since the graph contains 5 nodes, L is structured as an array of size 5. L4 corresponds to a linked list storing all edges originating from node E. And the highlighted linked list item represents an edge from node E to node D. Each linked list item can be expanded into an object to store additional edge-related information, such as edge weights. Since each node is stored as an array entry and each edge as a linked list item, the space complexity of an adjacency list is OV plus E. In a dense graph, where the number of edges E is on the order of OV squared, the space complexity becomes OV squared. On the other hand, in a sparse graph, its space complexity is reduced to OV. Hence, the adjacency list is well suited for representing large and sparse graphs. Next, we discuss the implementation of fundamental graph operations using an adjacency list. First, for the add node operation, a new entry must be appended to the last position of both V and L, as highlighted in red in the figure. The amortized time complexity for appending a new entry to an array is O1, so as the add node operation. Here is the pseudocode for add node. In lines 2 and 3, a new entry is appended to the end of V and L, respectively. For the add edge operation, a new item is appended to the end of the corresponding linked list, which executes in constant time O1. The newly added item is highlighted in red in the figure. The addEdge function takes 3 parameters as input: the source node index I, the target node index j, and the edge object E. In line 2, node j is recorded as the target node of edge E. In line 3, the edge object is appended to the end of the linked list Li. Next, we discuss the delete node operation. To remove node I, we perform lazy deletion by marking the entry Vi as null. Additionally, we also need to remove all edges associated with node I from the graph. This can be done by deleting Li and all linked list items representing edges that target node I. That is, the yellow array entry and linked list items shown in the figure. To avoid additional overhead, we do not modify the adjacency list L immediately. Instead, we determine whether an edge exists by checking if its endpoints exist in V. For example, when visiting a linked list item pointed by P, we check whether V P data source or V P data target is null. If either is null, then P refers to an edge that has already been deleted. When the null entries in V outnumber the valid entries, we shrink both V and L. Shrinking L requires visiting every element, taking OVD time, where D is the average node degree. Shrinking V and L occurs after OV node deletions. Therefore, the amortized time complexity for delete node is OD, while in the worst case, it becomes OVD. To track node degrees, we traverse Li to find all neighbors reachable from node I and reduce their indegrees. To identify all neighbors that can reach node I, we maintain a reverse adjacency list, L', where L'I stores nodes that reach node I. Thus, we reduce the arc degrees of nodes contained in the linked list L'I. Traversing Li and L'I both require OD time. Overall, the amortized time complexity for the delete node operation becomes OD. Here is the pseudocode for the delete node operation, which takes the index of the node to be deleted as input. In line 2, we perform lazy deletion of node I by marking Vi as null. In lines 3 to 6, we traverse the adjacency list L to update the degrees of all nodes reachable from node I. In lines 7 to 10, we traverse the reverse adjacency list L' to update the degrees of all nodes that reach node I. The next operation, delete edge, removes an edge by traversing the linked list of its source node. Once the corresponding linked list item is identified, it is removed directly from the list. This operation runs in OD time, as it needs to traverse a linked list. Here we show the pseudocode for the delete edge operation, which takes the source node index I and the target node index j as input. In lines 2 to 6, we search for and remove the linked list item that corresponds to the edge that needs to be deleted. In lines 7 and 8, we update the degrees of the source and target node of the deleted edge. Next, we have the update node weight and update edge weight operations. The weight of node I can be updated directly by modifying entry Vi in O1 time. To modify an edge's weight, we must traverse the corresponding linked list to locate the correct entry, which requires OV time. Below is the pseudocode for the update node weight and update edge weight operations. For update node weight, the weight of node K is updated directly by modifying the corresponding entry Vk in the node array. For update edge weight, we traverse the linked list Li to locate the corresponding item and modify its content accordingly. The next is adjacent operation checks whether nodes I and j are directly connected by an edge. To do this, the algorithm traverses the linked list Li to determine if an edge exists that ends at node j. Since this requires scanning the list, the operation runs in OD time, where d is the average degree of the nodes. Here is the pseudocode for the isAdjacent operation, which takes two node indexes I and j as input. In lines 2 to 6, it traverses the linked list Li to check if an edge leads to node j. If such an edge is found, I and j are connected. Otherwise, they are not. Then we have the list neighbors operation, which outputs all nodes that can be reached from node I. This is achieved by traversing the linked list Li, which requires OD time. The following is the pseudocode for the list neighbors operation, which takes the node index I as input. In lines 2 to 6, it traverses the linked list Li and output all corresponding target nodes. Finally, we have the getDegree operation, which directly retrieves the degree of node I from Vi. Since the degree is precomputed and stored, this operation runs in constant time O1. Here is the pseudocode for the getDegree operation. The table below summarizes the time complexities of fundamental graph operations using the adjacency list implementation. The operations add node, add edge, update node weight, and getDegree run in constant time O1. On the other hand, the operations delete node, delete edge, update edge weight, is adjacent, and list neighbors require OD time. When dealing with dense graphs, the average degree D is on the order of OV. The corresponding time complexities for fundamental graph operations are listed in the middle column of the table. For sparse graphs, the average degree D is on the order of O1. In this case, as shown in the last column, all fundamental graph operations can run in constant time O1. In summary, we introduced two approaches for graph representation: the adjacency matrix and the adjacency list. The adjacency matrix approach represents edges using a two-dimensional array, allowing for constant time edge lookups given the indices of the n nodes. However, it requires OV square space, making it inefficient for large graphs and difficult to resize. In addition, identifying all neighbors of a node requires traversing one entire row, regardless of the node's degree. Therefore, the adjacency matrix approach is best suited for small and dense graphs, or in scenarios where frequent edge lookups are required. It also works well when the graph is static, meaning node insertions and deletions are rare. On the other hand, the adjacency list approach represents edges using an array of linked lists, where each linked list stores the neighbors of a node. It does not support constant time edge lookups, as checking for an edge requires traversing a linked list. However, it is more space efficient, easier to modify, and supports efficient neighbor enumeration. These features make the adjacency list best suited for representing large and sparse graphs. It also works well when frequent neighbor enumeration and no insertions and deletions are expected. In conclusion, each approach has trade-offs, making it essential to choose the right one based on the specific application needs. Thank you for watching, and see you next time.